Welcome to lesson 1.2. This is about reflections and stretches slash compressions. So there's a slash here because these are just, it's really the same thing as stretch or compression. We'll be seeing that in just 1 minute. So just a couple definitions. First of all, what's a reflection? So the first thing a reflection is, it's a type of transformation. So I'm going to say it is a transformation. So other types of transformations we've already taken are the translations or the shifts, moving it left, right, up or down. So we've learned that from our H and our K values. Now we're going to be talking about reflecting. So when you think about reflecting, you can think about reflection from a mirror, and that is really a good way of describing what's going to happen. A reflection is a mirror image. So if you take some initial shape or a function and you reflect it. Okay, well there's two ways of reflecting that we're going to look at today, and the first one is reflecting over the x-axis. We'll zoom in a little bit over the x-axis. So if I have, I don't know, let me see if I can draw something here. So if I'll draw just a x and our y-axis, and then let's say if we have some type of a shape here, we'll define it just by a few points there. We'll say it has a shape like this. Now this is the x-axis, this is the y-axis. I kind of like the wet ink analogy. So imagine that this green stuff here was written with very wet ink, and now I'm going to fold the paper. And where do I fold it? I fold it across the x-axis. So if I'm looking again at this x-axis, if that's where I fold the paper, then where does this line, where does these points reflect? So this one reflects over here. I should really get a new color for that. So this one lines up over there, and then over here, and over here, and this one's kind of more over there. So you see we get a new shape. Okay, so this one was reflected. Here's the original, and then here is the reflected. Here's the reflection. And what is happening when we reflect it over the x-axis? Really what we're doing is we're multiplying. Do I have a place for this over here? Maybe I'll write it over top. We are multiplying our y values, multiplying y values by -1. Okay, so that's what reflecting over the x-axis looks like. The other one we could do is we could reflect over the y-axis. Alright, so let's try to replicate a little bit what we just wrote. Let's do another example, but here is our x and here's our y. And again, I'll draw my original. Try to draw it kind of similar. This cute little shape of ours. And now, just a reminder, this is the x-axis. This is our y-axis. We're going to do just like before. Again, we're going to think of this as having wet ink, but now when we fold it, we're going to fold it along this y-axis here. So this spot will end up over here. This spot will end up over here. And this is the kind of shape that we're going to get. Maybe I looked like I stretched it a little bit too. I didn't do that on purpose. So now this is our reflection, and of course this is our original. So that's what a reflection looks like. Okay. A stretch and a compression. So for defining this, so first of all, this is also equal to a type of transformation. A stretch means something is getting larger. And the compression means simply it's getting smaller. Okay, so, pardon me, we could have a horizontal stretch. So we'll start with an original. What color is our original? Usually green. Okay, we'll do green for our original. Again, some things a little bit like that. So now if you're doing a stretch, it's not a wet ink analogy. Now if you can imagine that this entire graph here is made out of rubber. So imagine that the paper, pretend you grab the paper and stretch it. Kind of like you wrote this on rubber and now you're making the rubber larger. So what happens here is that this, if we're going to do a horizontal stretch, that's along the X here, whatever distance this is away is going to increase. So in our image, we're going to get something that turns into, okay, so I kind of wrote it and it overlaps quite a bit, doesn't it? So this is what happens when you stretches it. So imagine if you take your two hands and do that type of a thing. For the compression, see if I can fit a compression in here. Instead of drawing the green one again, I'll just only draw the red one, and the red one's going to look like, you can see how it got very compressed, so it's making it smaller. We can do the same thing with a vertical. We can do a vertical stretch. And now, I won't draw the green one again, but you can see the vertical stretch doesn't change the horizontal distance or shape, just stretches it vertically. And then the horizontal compression, kind of something like that. We'll be taking a look at it in the Desmos, the graphing software, a little bit later as well. An invariant point. Invariant means it doesn't change. So in not great English, you could call an invariant point a don't change point. So an invariant point remains unchanged after a transformation. So even though everything else could be changing, an invariant point doesn't make a change. And in a good example, a good place to look is on a line of reflection. All right, so turning the page here. Here's a graph that's given, and we want to sketch these following graphs. Okay, so this first one, you'll notice that what we've added is this minus in front of the f of x. So really what we're doing here is we're going to be multiplying our y values by -1. So one way to map this is if x and y, using our mapping notation, is any point on our original graph, a corresponding point will be the same x value, but our y values will be multiplied by -1. So let's consider first of all on our original graph what our x and our y or f of x values are. Okay, so we have an x of -2, that's this one here, and then y is 0. We have an x of 0 and a y of 1. We have an x of 1 and a y of -1, and we have an x of 2 and another -1. So in this y is equal to the negative f of x, we're going to keep the same x values, but our y values are going to be multiplied by -1. So I can just copy out my x, -2, 0, 1, and 2, but now I'll do the opposite. And you notice this is 0, the opposite of 0 is still 0. Here I get a -1, +1, and a +1. So you know what? I'll use blue here because I wrote this in blue. So this will be our y is equal to negative f of x. So when x is -2, we still have that same point. When x is 0, instead of +1, we have -1. And now when x is 1, instead of -1, we have +1, and we have +1. So this is the way joining our dots now. Okay, so in blue is our y is equal to negative f of x. Could you spot any invariant points? I'll use IP for invariant points, so there's one. And here's one too. This one didn't change. Okay, so in fact, anytime where it's on this x-axis, it would not change, right? Because when something is on the x-axis, it means that the y value is 0, and when you're multiplying 0 by -1, it doesn't change. Okay, maybe switching to green now. Let's think about this one here. In our mapping notation, if x comma y is a point on our original, now the corresponding point will have a negative x because of this negative x, but the same y value. So when I'm drawing my chart here, okay, this will be x and this will be y is equal to f of negative x. In order to get the same result, because x is going to be multiplied by -1, I have to input an opposite x. So this -2 is a 2. So if I plug a 2 into this function, then a -2 gets plugged into f of x, and then I get a 0 that comes out. So I have to kind of undo this negative effect of that x to get the same result in my y. Shorthand, take all these x values and write their opposites, and keep the y values the same. So that's what this kind of mapping notation really means in words. It would be any point xy in our original, say -2 comma 0, in this y is equal to f of minus x, multiply all the x values by -1 and keep the y's the same. So now when I graph this, oh, I was supposed to graph it down here. Okay, oops, so I'll graph it on this bottom one over here. My x value is 2 and my y value is 0. My x value is 0 and my y value is 1. My x value is -1 and -1 and -2 comma -1. So now when I draw that, so you might not see that right away, but when you think of, hey, I take my the dash and this faint dash, that's the original function, and you can sort of see that that concept of multiplying by -1. So this line got reflected and went over here, and then this line here got reflected and got over here. So this is got reflected over the y-axis. So it's kind of interesting. When I multiply my x values by -1, it reflects over the y-axis. Okay, so we'll do a little summary here. So first of all, this was y is equal to f of -x. So what we do in this case is that we multiply the x values by -1, and what this does is it reflects over the y-axis. Okay. Similarly, over here in our y is equal to negative f of x, having that negative on the outside of the function, this multiplies our y values by -1, and that causes reflection over the x-axis. Okay, so I hadn't drawn it really. I drew it over top of it. So if I was to draw it here, there's a reflection over the x-axis, and this one is a reflection over the y-axis. I'm going to pause there, and then so you can take a little break before you start the next page.